Another draft physics video presentation. Should be anyway. Alright, so I figured I'd play the Feynman video. I've played it before, but it gets easier. The more you understand, the more you can understand what he's saying and why what he's saying is wrong and why they all went wrong. And so I've sort of been over some of this, but it goes back to just the mistake of religion, frankly. You could argue that was the first mistake physicists made. People who wished to understand how the world worked, they just drew some wrong conclusions about what they saw and their deduction. You could argue that things like finding shells on the top of a mountain, this is the kind of thing that, somebody did it before Darwin. Darwin wasn't the first person to observe there's a bunch of seashells on the top of mountains. And you could understand that they would come up with some idea that a flood happened and the water was as high as the mountains at one time. Because they could understand that mud turned into rocks and, the fossils. They could sort of make these deductions. But they couldn't explain what they were doing up there. They couldn't really imagine that the mountain pushed out of the earth. I mean, that seems the less likely scenario. So they knew what a flood was. They knew, what these things were. And so that was the more logical conclusion at the time. But with a little bit more information, they find out, oh, okay, yeah, the mountains actually did get smushed out of the ground and pushed up. And, it's not so mysterious. You find a better explanation, and you have to wait for it. And there's always, this process has always been kind of difficult. The battle between, say, the religions that were like the stories told about all the animals being the gods, and they became kind of out of favor. And so then you had a bunch of religions that had more to do with spiritual things in a heaven someplace controlling us, and but then you could see that the religions sort of gravitated away from the religions controlled by demons and Thors, and all kinds of intrigue between the gods, and then you have this one god, and these are all just versions, stories, and the ones that are more plausible to people's taste at the time, or what their knowledge base at the time, and and this is just part of that process. Is what did physics do? Well, it took something that was a 300-year-old mystery. I mean, a Newton mystery. That is, light does something funky when you put it past impediments or through holes or against surfaces, or it does something not expected. You find some sheath shells on the top of the mountain, so to speak, and you have to explain where they came from. And the other process was just this basic thing of light that surrounded people all the time. And, what's it doing? How's it do what it does? And so you try to do different things. You try to create a shadow, and what does the shadow do? And try to figure out what it is. So Newton did the obvious, makes a shadow. The shadow has a line to it. If it was waves, it would go around the line because waves like to do that. Different ways of interpreting it, but even these words don't really mean anything. So we can go back to the whole question of what light is, and as a context. And so you have this thing that's obviously the source of light, and the question is the light being produced as some sort of thing that waves? Well, what's a wave? We know in water, right? I mean, maybe they didn't know this 1,000 years ago. Maybe they didn't know it 500 years ago. But we sort of know now that a wave isn't really a wave of anything. It's really pressure, and the pressure's in little points. And all you're really saying is that, yes, little atoms bang into little atoms and bang into little atoms. And you can interrupt this wave. You can do a lot of things to disrupt it by disrupting the source. But, this idea that it has to be a medium, well, it doesn't have to be a medium. You can create the same kind of pattern by just shooting little stuff from all these points and just having them, here's a piece, here's a piece, here's a piece, and flying through space, here's a piece, here's a piece, here's a piece, and the same thing will happen. And the only difference is in water, you have a substance where the little atoms are connected to each other, so there's this continuity between them, and so they'll fill in all the gaps. So if there's any gaps, they'll fill it in. They'll stretch and pull and create. They'll simulate the missing pieces, so to speak. They'll fix any kind of irregularity. Where if it was actual particles, then again, then you have the sharper lines of a shadow. Where the shadow is cast, and there's a kind of a hard line because it doesn't fill it in very well or very much. But anyway, and so then you think, okay, so this idea of whether it's clumps or whether it's some kind of bent medium. So there's already an existing medium, and somehow you're making the medium do something. You're causing a perturbation. But it doesn't make that much difference, right? I mean, the two still come down to, this is energy moving in a direction, and that's the primary function. And the energy going this way isn't making this wave, and the energy going this way isn't making this wave, part of it. The energy has to be there, or it's not going to be a very good wave. All right, so the competing theory is that you have a source, and it is just shooting things. And it shoots them all at the same time, and it shoots a bunch all at the same time, and it shoots a bunch all at the same time, and it just creates something that, okay, if I walk far enough away, this is what I'll see. Okay, I'll see the pattern. Okay, it'll look like a wave, but it's not a wave, really. There's nothing waving. These are all individual soldiers, moving towards the German line. They're not tied to each other with ropes. They don't. If one of them dies, he's dead. Okay, the other guy. These guys don't fill in the void. They're just individual bullets. But then, okay, so then you have this vision of a bullet moving at a frequency, and I can draw it like that, a bullet at a frequency. But what's a photon? Is just one little bullet a photon, or does a photon have to be something more than that? And so then there's another argument about understanding that if I use the word photon, I have to say that a photon is something with a frequency, that it has to have parts to it, because the only way you can have a frequency is you have to have more than one of them. The thing itself, the photon, isn't this, right? The soldier isn't doing this. This isn't a soldier, and then this is a soldier, and then this is a soldier. No, there's soldiers with distance between them. So these are just easy little different versions. Now I'm going to argue that, this vision of the soldiers being separated by a distance, this is the right answer. Okay, the right answer is this is what a photon is, and that it takes a number of these before you call it a photon. So a photon is a composite object. Yes, it's a particle. I mean, obviously, it's made of particles. Okay, it's not a wave, and the particles have a little slight out of arrangement. Okay, I've discussed before. Always something. Because they're produced by an antenna inside the atom, and that's another kind of. Again, I'm jumping so fast, through the history. But I mean, this is the polarization. That makes sense. They're a little bit out of alignment because they were created by an antenna, like all antennas, and the antenna's creating them at a different time. This one first, this one first, then this one, then this one, then this one, then they all go different distance. They're a little bit out of alignment. Anyway, and so now you understand what the package called photon is. It's a ray, of light, and the ray has a length, and it has the frequency is built into it, and this explanation satisfies. So this is the right God. This is the evolution theory versus the mystical ones, the notions of magical big giant long blobs of stuff flying through space, giant particles, or the notion that there has to be some sort of fluid that the photon is flying through, and like I said, the lack of evidence of any adhesion between photons. Like photons want to stick together or something. There's no evidence they want to do any of that. They have any charge properties, none at all. So this is the right answer. So start here. And even if you're going to say that physics has reason to believe it should start here, science should be, well, we're going to keep this in mind, though. We're going to keep comparing these two theories and seeing which theory explains more, which theory works better. And then you get into things like these experiments where it gets kind of tricky. You can be fooled easily. Seashells on a mountain. And you're going to have to do a little bit of, investigating to find the right answer. You're going to have to pick at it a little bit. You're going to have to go down the shore and see that, these fossils are made, and there are fossils, that the earthquake happens and I see the land moves, great distance, sometimes hundreds of feet. You can see you go to an earthquake fault, you can find where there's hundreds of feet of difference, where the ground is way up there is the same as the ground way down here. And that they change position. So you find little pieces of evidence that make it more possible for you to understand that the mountain rose, and that the little seashells were made in an ocean that wasn't a flood, okay, and they were taken up there, by the geology. And so I'm arguing that, yes, you can see that physics has made these obvious bad conclusions. They've committed to some bad ideas. So I shall pause for a moment. Alright, should be back. Alright, so, this whole argument is that they think they've, excluded the mountain popped out of the ground, moved, and it's up here because they think they have some theory that proves that that can't be the right answer. Has to be some other answer. Has to be, one of our wooier answers. Our religious answers. Our demons are in play because we have somebody drew one, and they saw it and they drew it right away, and so we have a picture of a demon, and therefore the demons must be a real thing. I'm just arguing that those arguments where they say they've proven or they've demonstrated beyond any kind of reasonable doubt that the only way you can explain this thing is you have to explain it with this QM magic. It has to be some sort of the universe is playing dice with us and blah 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 blah, which is even a bad example, right? Because we know dice isn't random. We know it's not magic. So we don't even have an analogy. We don't even have a proper analogy for what a random source of anything is, because there is no such thing. Okay, and so it's just so ironic that we don't even have vocabulary to explain these gods in any kind of rational manner. Just as they don't have any explanation for how they're magical gods. Who made the gods? The gods are supposed to be an explanation for the function, and yet they don't have a function for what makes gods. So anyway, yes, this is just an argument about the weight of the evidence, which I've argued so many times, and you can just look at their evidence and see how incredibly unmiraculous it is, and how underdone it is, how blurry and fuzzy their little cigar UFOs are. And they have a whole theory based on those images. And it's really bad science. And, the people who are so hostile to conversations about these fundamental conclusions, and so insulting of anybody who questions the certainty of their uncertainty. Right. So this is probability and uncertainty, the quantum mechanical view of nature, and I would call it just the unmechanical, because that's what Feynman's directly saying at the end of this video. He's overtly saying it. No, it's magic. There's no way to explain it. It's magic. There's no mechanical system. There's poof, 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 poof. So it's the poof mechanical view of nature. great floods. Has to be a great flood by a great God. Can't be that mountains popped out of the ground. Was pushed up. Yeah, pushed. All right. So, with that context, leave us begin.
In the beginning of the history of experimental observation or any other kind of observation on scientific things, it's intuition, which is really based on just experience with everyday objects that suggest reasonable explanations for things.
Right, and so we all can agree, any intelligent person can agree that intuition is a little dangerous, right? That you shouldn't do this judge it by the cover kind of stuff, that you should go a little deeper, and that there will be things just from another one of our intuitions is our intuition to be cautious about intuition, because we find out there are things that have more complex answers. It looks like a woman, oh, but wait, it's not quite. Okay, a little bit different. Those kind of things can happen, and those are real things, and seems like isn't is like. Seems and is are two different words, and equal sign and not quite equal sign, kind of like, not exactly the same, and that it's a little dangerous to mix those symbols up to say you know it for certain when you don't really know it for certain.
But as we try to widen and make more consistent our description of what we see, as it gets wider and wider and we see a greater range of phenomena, the explanations become what we call laws instead of simple explanations.
So these are this idea just becomes edicts. So I wouldn't call them laws. I'd call them edicts. I'd call them draconian statements that you must be obedient to. They're converted into dogma, into the doctrine of the religion. And then it just becomes, this guy's wearing a certain kind of little Pope hat, and then there's other people wearing, Copenhagen Pope hats, and everybody has their little different little Pope hats and their little religions, and they're all fighting with each other over what the real true God is. And again, I would argue that any intelligent person should be looking for the Darwinian alternative, the nice, simple, mechanical explanation, right? I mean, quantum mechanics is not mechanical. It's not a straightforward cause and effect explanation of reality. It's a magical explanation.
But the one important odd characteristic is that they often seem to become more and more unreasonable.
Right, now that's part of our intuition, right? Exactly. So, we know how unreasonable the silly Bible stories are. They're just wacky and silly. They don't make any sense at all. People swallowed by whales. Whales have a throat that big. Wacky, silly nonsense.
More and more intuitive.
Well, except for great white whales have a much bigger throat.
Far from obvious. To take an example, is the
killer whales, great white whales. What the fuck? See, mythology gets mixed up even in our references. The mythology shows up. The boogeyman, the gremlins.
The relativity theory, in which, for instance, the proposition is that if you think that two things occur at the same time, that's just a subjective opinion. Someone else could conclude that those two events.
Okay, and so this is a perfect example. So he's using it as an example of when intuition is wrong. Okay, an example that's just crazy, right? It's an example of another silly theory that is in fact just nonsensical mush, right? So, he's using it as an example of how we get it right when it's an example of exactly getting it wrong, right? Because you have this simple intuition that, no, there's two events that can happen at the same time. They happen at the same time. Boom, two events. And now, because a person can stand here, or a person can stand here, or a person can stand here, all of a sudden we're going to say, no, these two events aren't real events anymore. The reality is what does this asshole see? Or what does this asshole see? Or what does this asshole see? That's reality. Reality is somehow a mixture of this, plus or some kind of crap like that. No, the reality is this. This is the underlying reality. It's not about whether I look down at something, or I look at something sideways, or I look something from below. We know that doesn't change what the elephant is. The elephant is an elephant. He's sitting there elephanting. I am an elephant. he doesn't give a shit about, oh, yeah, I'm looking at you from over here. I'm looking up your butt. I'm looking at your ears. He doesn't care about any of that crap. This is the reality, and the reality is independent of what these idiotic observers are doing. It doesn't have anything to do with the reality. Their perception doesn't change the reality. The spontaneous events are spontaneous, instantaneous with each other, are in fact that. Instantaneous, it's that. Simultaneous. The simultaneous events are simultaneous. You don't change it by saying, well, I looked at it from here, therefore the two events aren't simultaneous. Bullshit. It's so stupid as an example of how, we catch ourselves being wrong. No, this is exactly the trap. You fell for it. You went for it. Somebody give you some jargon and you sit there and fell for something completely stupid. That somehow these two events, this reality isn't a reality. It depends on who's looking at it. No, it doesn't depend on who's looking at it. It's just nonsense. That's just so bad. That's falling for crop circles. It's just such bad analysis. You can just see on the face of them, this would be easy to do. This is pretty easy to fake.
Those two events, one was before the other. And that simultaneity is merely a subjective impression.
Yeah, no, it's not merely a subjective impression. It's a physical thing that happens in the physical real universe, and you've decided that somehow you can break that reality and somehow have coexisting theories of nonsense or statements. 2 + 2 = 3 over there, and 2 + 2 = 7 over there, and no.
Now, there's no reason why this should be otherwise, really. The things of the direct everyday experience involve large numbers of particles, or involve things moving very slowly, or involve other conditions that are very special.
Well, the truth is we do see a lot. So we see a huge range of reality. And obviously, I think it makes sense that there's going to be things too big for us to see, okay, because they're so big, and things that are too small to see because they're too small. But we collect a range of experience out of a big hunk of the reality. It's not an insignificant amount, and there's no reason for us to suspend what we have learned by existing into starting to believe in gremlins and demons. There's just no reason. There's no room for them in a rational investigation. There's no good reason to believe that old ladies fall in front of cars because demons push them.
And represent, in fact, a very limited experience with nature. It's a small section only that one gets of natural phenomena from a direct experience. It's only through the refined measurements and careful experimentation that we can get a wider vision.
Okay, right. Now, that sounds like a really nice scientific statement, and has nothing to do with any process they go through. Their examination is superficial and mostly just they heard a story. They heard about an experiment with detectors. They heard about some kind of thing that happened. It never happened. So their investigation is so shallow. It's just as I just explained. They never really did even the simple thing that I did on the board, where I'm drawing a wave and I draw a ray and I try to figure out, well, what would the ray look like? What would the ray have to be? What would the wave have to be? What is it really made out of? What is water really made out of? Why does water behave the way it does? Those are such superficial mechanical explanations. And I'm saying to you overtly that what's missing is these people never even did that. They never even contemplated drawing it mechanically, understanding how it actually, what they could understand. They didn't even look for those answers. They jumped to the demon answer.
And then we see unexpected things. We see things that are far from what we would guess.
So again, this is all based, 90% of this whole quantum mechanics is invented out of something Newton discovered, okay? They didn't have great explanation for it. You make a hole, okay, you shine light through it, and this weird crap starts to happen where, you know, you end up with these rings of light rather than just, you know, light going through. So it's not just that the light does this, it's that the light does this weird crap, you know. And you do it with an impediment and the same phenomenon takes place. You end up with this weird pattern created where the light's on and off and on and off and on and off. Okay, it's not, there's something, this doesn't say that that should be the answer. Okay, this doesn't say that this should be the answer. But the simple part, one of the most basic parts of what's actually happening is that you can understand. Is that if I make this little hole smaller, I make this wider. And if I make the hole bigger, I make it narrower. So clearly you can say well, what's changing? Well, the odds of a photon interacting with the surface increases as I make the thing smaller. You know, and so they help create the whole Heisenberg thing out of this notion that somehow this is a measurement, and because you're measuring the photon, it doesn't like it, so it goes more erratic. You know, yeah, the obvious answer is no, it's more likely that the photon is interacting with this surface, and it is interacting with this surface. The closer I bring the surfaces, the less this ability to go through here without being close to a surface gets more and more difficult. And so you just increase the odds that any photon that goes through is going to be close to a surface. The smaller I make the hole, the more likely it is the thing that's going through is going to be really close to a surface. That's the obvious deduction. That's the big, giant elephant in the room deduction. But instead they turned it into Heisenberg demons, or forcing the photon to reject this measurement. I'm not going to be measured. I will not allow you to know where I am. Blah, 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 blah. I have to, you know, do something magical to escape, you know, identification. Nonsense. Just nonsense.
We see things that are very far from what we could have imagined. And so our imagination is stretched to the utmost.
So again, they had from Newton like 270 years to rationally explain something. And what did they do after 200 and plus years of looking at it? After 200 years, they come up with this wacky notion that the universe is random and the photons split in two, and they do all this bullshit. I mean, so, and I'm supposed to believe that they honestly tried to find a rational solution to the problem? No. Bohr was a religious nut, period. And he defined physics.
As in fiction, to imagine things which aren't really there. But our imagination is stretched to the utmost just to comprehend those things which are there. And
so again, it's, yeah, these are all tough problems. Like I say, I mean, yeah, you find the seashell on the mountain. It's pretty hard if somebody hasn't explained, you know, the Earth, you know, and moons and other things going on. Lots of stuff moving around, but it's moving really slow, but it's really, really heavy. You know, really slow, but really, really heavy matter. So it's really, really massive that, yeah, it could do all kinds of deforming. The little local seashore could get a little bit bent up, you know, when it's a whole giant continental plate moving.
It's this kind of a situation that I want to talk about tonight. Start, for instance, with the history of light. At first, light was seen to behave, it would appear to behave very much like a rain of particles, of corpuscles, like rain. Bullets from a gun, same idea. And then with further research, it was clear that it was not right, but that light actually behaved like waves.
So I'd say that there isn't a whole lot of reason to believe the wave theory, but whatever. Okay, it's you have to strain reality to find it. Just in the sense that clearly you can even speculate about light traveling from a distant object and how it gets to your eye, and it, you know, stretches credulity to imagine that this thing that lands in my eye is really just part of some giant thing that goes around the whole universe, and that those aren't individual soldiers. And again, let's understand the inverse square law is just, you know, that's a law that just became, you know, so obvious with gravity. And light is obeying the same law. Okay, and again, it's just so, it makes so much sense to understand that if I did send little bits out of guns, on a surface, that the further away I go, the little bullets are going to be getting further and further and further apart from each other. And they're going to be doing it in the square dimension. Okay, they're going to be doing it both width and height. So they're getting further away this way, and they're getting further away this way. And that's the R squared rule. It makes the R squared rule. The little guns shooting bullets off of this small object, at a distance, the little bullets will do exactly what the inverse square law says will happen. The other idea is that you have to stretch a wave in both directions. That your wave leaves, and somehow it maintains its integrity. It stays the same, stretching, not only getting bigger and bigger and bigger. We know that water waves run out of energy, but these photon waves can't run out of energy when they actually hit. There's the same amount of hit. The same hit you get here would be the same hit you get here, would be the same hit you get here. Now, how is that possible for this big giant thing covering all this space to have the same energy as this thing? To hit one point with the same amount of energy. How can this have the same amount of energy when it's spreading this way and it's also spreading this way? How does it have the same exact amount of energy? So there's real hard reasons to understand it. This doesn't work. This wave thing doesn't create the same effect nearly as efficiently. It requires all kinds of bending of reason to think that somehow the same energy is spreading over this gigantic space, because it has to deliver the same amount of energy to this little spot that it delivered at this little spot. It doesn't make any sense, a wave theory.
Like water waves, for instance. And then in the 20th century, on further research, it appeared that light actually behaved in many ways, again, like particles. In the photoelectric effect, you could count these particles. They're called photons now, and so forth.
Yes, they're called photons, but again, understand that word isn't defined. Doesn't mean anything. And even the wave people aren't dealing with it. So let's understand that this is supposed to be our real sophisticated smart physics, where we've done this investigation and we've analyzed the fossils and we've taken a good look at them to make sure, and we've done all this stuff, when clearly they haven't thought about it at all, because they'll keep showing you this idiotic picture of a photon, as some kind of thing, and they won't tell you, well, what about, is this a photon? Can I have this little hump? Is that a photon? Or is this a photon? Or is this a photon? What the hell's a photon here? They haven't even answered the simplest of questions. And then their polarization is well, it's two fields. It's polarized. One field is moving up and down, and the other field is moving in and out. Okay, so what they have to come up with is some kind of crap. Well, this is the polarizing field. If the electric is the one that's polarized. You see, in the magnetic one, it is going this way, but this polarization is really, really small, because the magnetic field is incredibly weak compared to the electric field. So therefore, it's only blah, 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 blah. It's only going fat this way a little bit. So even though they draw it like this, there's no evenness between the two fields at all. One of the fields is almost a straight flat line. So it doesn't make any sense when you force them to explain. It doesn't make any sense. So it's polarized this way, but this polarization doesn't mean anything. That's kind of nonsense. It doesn't work. A little bit of drawing, a little bit of analysis, and you can see how it doesn't work.
Again, electrons, when they were first discovered, behaved exactly like particles, bullets, very simple. Further research shows, in electron diffraction experiments and so on, that they behave like waves.
So again, not true. It didn't show any such thing. It just showed when they did a trick. So they did a trick and said velocity is the same as frequency. So you are judging something's momentum, the momentum of an electron. Okay, so the speed at which the electron is traveling. That is, say if there's another electron here, you could understand that the faster this electron moves, the less it'll be deflected by this electron, right? So the slower it moves, the more the two electrons, the more time, like two magnets, they'll have to repel each other, right? And the faster it moves, the less time it has to repel. So it's just like gravity, in the sense that you understand the faster the object's going, the less the gravity has time to affect it, and the less it's going to be affected by the gravity, the less it's going to be bent. And so they equated this, its momentum, speed, with an amount of bending, and just made this comparison to the fact that, well, a higher frequency light, okay, has more energy, okay, because obviously there's more soldiers, okay, the tighter the frequency, I mean, the closer you put the frequency, the more soldiers you end up having, obviously. And the polarization gets narrower, that is, the soldiers hit a smaller area. So the wider the polarization, the wider the area the soldiers are hitting, plus there's less soldiers. So obviously there's a correlation between energy, okay, and frequency. But frequency isn't energy, and momentum is. And they're two different things, but they just made this correlation. They said this is similar, okay, close enough. Momentum is close enough to the effects of energy, and so therefore we'll call this a frequency. It's momentum, but it's not a frequency. Electrons have no native frequency.
And as time went on, there was a growing confusion in the question of how the things really behave, the waves or particles or waves, but everything looked like both. Now this growing confusion was...
Right, and so again, it's not a confusion, it's an argument, I suppose, would be a better way to state it, right? I mean, I don't know if there were too many people who were actually on no side. They really were confused. They really were like, I can't say. There were people who either did some diagnosis and they said, well, waves just can't make sense. I mean, you can't spread the energy over a giant area, end up with exactly the same amount of impact at a point. So that doesn't make any sense. But yeah, bullets, you can hit a target, right? If I make the target further and further away, smaller and smaller, you can understand the odds of hitting the target are less and less. It's harder and harder to hit the further away the target is. Yeah, duh. It explains perfectly the phenomena. And so, yeah, somebody who was thinking, there's no way, okay? It's particles. So it's an argument. It's a controversy. It's not a confusion.
Resolved in 1925 or 26 with the advent of the correct equations for quantum mechanics.
Right, so this idea that their equation solves a problem is just more nonsense. The equation doesn't solve anything. It's just a statistic. It's a way of doing statistics, and it's all it is. Okay, nothing else. It's just a way of recognizing that we know there's an outcome. It's either the bullet hits or the bullet misses. All right, we know there's a probability. The further away the target goes, the higher the probability of a miss, and so you come up with an equation that basically you just feed that information in. We know how accurate our gun is, and so we're basically just saying that, yeah, you put the information into the equation, give it some symbol, call it something. Oh, this is the wave equation. No, it's not a wave equation, it's a probability equation. And you put the information in, you give it the information about what the outcomes are. You observe the outcomes, put them into the equations, and then say somehow I proved something or I predicted. Well, of course you predicted because you observed, and you already told us what the odds were. You already had to glean those. That's what this symbol means. Find out what the odds are. That's what it means. You didn't predict the odds. They find out what they are, and then they predict the outcome. Yes, of course they predicted the outcome because they sat there and observed the outcome. There isn't no magical equation that solves anything. This is just such a perversion of reality, is to say this little forky symbol tells us. It's a telescope, it's a microscope, it gives us some information. It gives nothing. it really is literally this stupid. You watch the roulette wheel, right, and you see the outcomes. You write them down on a piece of paper, and then you say, I have an equation that'll predict the outcome. You know, just as a generality, that 10% of the time this will happen, and 10% of the time this will happen, and 10% of the, you know. That's not magic. Observing and then predicting is not magic.
And now we know how the particles, how the electrons and how light behave. But what can I call it?
So again, yes, they don't know how it behaves, and that's why they can't call it anything, because they have no clue what the cause and effect reasons are. They don't know why the dice come out random, in the sense that how come boxcars happens just as often as snake eyes? How come? You know, they don't have any explanation. They just know it does. And they're very proud of themselves that they predicted it after rolling the dice a few thousand times. They actually predicted that there's a correlation between the two, that there's an equal probability of the outcomes, and they make it sound like they knew it by some theory that gave them that answer. Didn't give them the answer. There's no formula that says, Jesus, stop it. That's going to that actually does predict. You have to tell it what the environmental circumstances are. You have to tell it what the thing that's happening at a probabilistic rate is, whether it's a cycle, whether it's a, you know, whatever the thing is. You have to tell it the answer, essentially, for it to get the answer.
I can say they behave like a particle wave, or they behave in typical quantum mechanical manner. There isn't any word for it. If I say they behave like particles, they give the wrong impression. If I say they behave like waves, they behave in their own inimitable way.
So, and he will say later that way is that they poof a random position in space. They poof their identity. It just happens. Okay, they go from being this to going to being this for no reason. It just happens that they decided to go from this place in space to this place in space, and they just instantaneously, spontaneously jumped there by magic. And there wasn't some process that forced them there. And that's supposed to be, oh yeah, the evidence is so conclusive. Yeah. But that's their theory. That's his theory.
Which?
It's, you know, there's no mechanical function. There's just magical randomness.
Technically could be called the quantum mechanical way. They behave in a way that is like nothing that you have ever seen before.
So again, he's saying it's like nothing I've ever seen before, but I kind of have seen examples of this kind of stuff before. I mean, you can do these simple analogies to electricity and water pressure, and, you know, those analogies hold pretty tight. And certainly this idea that if I'm got a hole and I'm going to try to squeeze through it, I can certainly understand that if I miss the very center, you know, that, oh yeah, my shoulder might get knocked off over here, might get torn right off my arm, you know, my arm might just get torn right off, and gee, I'm going to be without an arm because my arm's going to get torn off. And if I, you know, we can certainly know from personal experience how hard it is to shove something, a square peg, through this round hole. You know, we know that the square peg, oh yeah, all these edges might get ripped right the hell off. That something might happen. The smaller I make the hole, the more difficult it gets. Say if the square is just this size, you know, the more difficult it gets to aim it well enough to get it through the hole. So you could certainly understand that there could be some relationship between light and the surface, and that this surface might be doing something to the light to make it go in these directions. That's hardly some stretch of bizarre imagination. No, it's very understandable. I don't need a magic demon. I don't need some magic randomness to say, ooh, I made the hole smaller and therefore more of the stuff flew out funny. And it's because I've increased randomness. No, I've increased interaction.
Your experience with things that you have seen before is inadequate is incomplete. The behavior of things on a very tiny scale is simply different.
So he says it. He says it overtly. No, there's no mechanical explanation. There's no reasonable explanation. We have to believe in the magic demons. Only demons push old ladies in front of cars. It's obvious.
They do not behave just like bodies. They do not behave just like waves.
Well, frankly, they do behave just like particles if you understand that it's a composite. You know, the particles are what the thing is made out of, is the quanta part, the Planck little bit, the indivisible object that has the minimal properties. The dice. We're just talking about the dice. The dice are solid mechanical things. I'm going to throw them into a mechanical system. They're going to do mechanical things, and then they're going to have an outcome where they stop, and the photon is doing the same thing. But the argument with the photon is you don't never kill a photon. You just transfer its energy from place to place to place to place.
Atoms do not behave like weights hanging on a spring and oscillate, nor do they behave like miniature representations of the solar system with little planets going around in orbits, nor does it appear to be somewhat like a cloud or fog of some sort surrounding the nucleus. It behaves...
So he just ruled out all of these things, okay, with this idea that even the cloud theory, you know, which is so common now, of this amorphous position changing thing, even saying that's not true. So he's saying there's no cloud, there's no superposition, there's just jump, there's just magical change your identity thing, there's just magical gremlins that push the thing to some other place. You know, that's, it's just, but yeah, so I'll draw for just the sake of understanding that we understand that a spring, we understand all these systems now, and we understand that they run out of energy, that they don't, you know, they can't do something perpetually and all this kind of stuff. So we do understand something about how energy works and gets into a system, a box, okay, and that it can do all kinds of things while it's in the box, and that there will be eventually an equilibrium or something else, and it will leave the box, and that this can have a certain temperature, and it's maintained because new things go into the box while this thing leaves, this thing comes in, and we just maintain the same temperature because the amount going out is the same as the amount going in. But we can sort of do this idea that it's sort of a known idea in physics that the energy doesn't ever die, that you can't kill it. It's just forever energy. And all you do is you connect it to something else, and the energy can go from this system into this system, and it can stay in this system for a while, and it can go into another system, and another system, and another system. The same energy that was making dinosaurs walk the earth is the same energy that's making us make videos about physics. It's just the same stuff, making cause and effect changes in things while things are occupied by it.
It's like nothing that you've seen before.
So again, I've seen it before, you know, in Bibles, you know, demons, you know, hobgoblins and such.
Well, there's one simplification. At least electrons behave exactly the same in this respect as photons.
So exactly the same. This is another one of these things where, you know, they don't really have all these experiments, right? I mean, electrons are terribly, insanely small things, okay? So I can't even describe this. They're so preposterously tiny. And as I've pointed out, the polarization of light, just the distance, the height of the wave of a light, right, is a million, well, probably 1 billion times, maybe 1 trillion times. So this distance of the wave of the light is 1 trillion times bigger than the diameter of an electron. 1 trillion times bigger. You know, and you know, so again, if they just drew this stuff on a blackboard, they could figure out it doesn't make any sense. Okay, that, you know, what their theory is of how this is working can't possibly make any sense. But clearly, you can't test this thing. I can't hit it with a beam of light. I can't hit it with something 1,000,000,000,000 times bigger than it. Okay, and then have that bounce back by some sort of magic and tell me where this electron is. Because we already know it's going to move the electron. And I certainly can't make an experiment where I send an electron that we know is negatively charged at plates or surfaces of any kind, because we know those surfaces are charged, and we know this thing is going to get screwed up by the charge on these different atoms, that we can never make a charge so perfectly neutral to ever fool an electron. So there's no, this is to say, oh, they're exactly the same. It does exactly the same thing. As I pointed out, when we, even to move an electron, to give an electron momentum, we have to do it by basically creating a device. We have to create something that radiates a lot of energy, okay, to move the electrons in a direction. We have to push them, frankly. And there's X-rays, and there's all kinds of different rays of radiation flying out of this object that we're pushing the electron with, obviously. So the very idea that we sit here with our little detector and say, I can see just the electron. I don't see any other energy hit this thing. It's difficult to make substances that could see just electrons and nothing else. Okay, like the TV screen is doing. TV screen's basically doing that. It's saying, I only see electrons. Okay, I'll only light up when you hit me with a real hard electron. But what's going with the electrons is a bunch of radiation. That's why it wasn't too safe to sit there with your face right up against the screen. It's because there's a bunch of X-rays and other kinds of rays flying out. It's certainly flying on the other side of the glass. Okay, I mean, some of this stuff gets blocked by the different screens, and so it's disrupted. The microwaves are disrupted by the little holes in the microwave oven. So you break the rays, and when you break the rays into little pieces, they can't do the same kind of damage. But the truth is all this radiation is pushing the electrons. So there's a bunch of rays, I would argue, there's a bunch of rays of light flying off, invisible light, flying off of the heated element that's producing the electrons. And the electron, we can move it in a magnetic field. So I can create a bunch of wire, and I can move it, or I can move it right here at its source, in a direction, because it's charged, so I can move it. And all I'm doing is moving it to different rays. I'm just pushing it to some place where it's going to get hit with a different kind of ray. But the rays are pushing the electron. The electron has no momentum on its own. It's being pushed all the way to the screen. And that's why it takes a tremendous amount of energy to push these tiny little particles in accelerators. It's because you have to keep throwing a bunch of rays at them to keep pushing them. All right.
That is, they're both screwy, but in exactly the same way.
All right, so that's the extent of it. Screwy, but it's screwy that there's seashells on mountains, the top of mountains. It's screwy, okay. But we can answer the question rationally. We don't have to come up with these green giant, put them there. Green giant like to. Shellfish, and he ate a bunch of them on top of the mountain and dropped all the shells there. I mean, we don't need to come up with some silly theory.
How they behave, therefore, takes a great deal of imagination to appreciate, because we're going to...
See, it takes a great deal of imagination, I suppose, to go through all of these little details, to draw all these different pictures and see which picture makes sense. Green giant, gremlins, UFOs... are physical causes and effects. Yeah, which one should I choose? The silly answer are what I know is going to be some underlying mechanical explanation.
Describe something which is different than anything you know about. This, in that respect at least, makes this perhaps the most difficult lecture of the series, in the sense that it's abstract.
Yeah, and I have to make up cartoon characters and magical forces, and I have to say things like, well, we have a perfect theory that predicts everything, but it can't explain a goddamn thing. It can't give you a single cause and effect reaction. It just says there is no such thing, and Gremlins did it.
In the sense that it is not close to experience. And I cannot avoid that. Were I to give a series of lectures on the character...
So I'm just saying it isn't that far from personal experience. Like I said, the idea that an aperture gets smaller and it becomes more and more likely that something's going to be affected by the surface, there's nothing unintuitive about that. There's nothing that strange about that. There's no difficulty in explaining why there'd be a relationship between the strange behavior and the fact that the surface is becoming more and more unavoidable.
Physical law, and to leave out from this series the description of the actual behavior of particles on a small scale, I would certainly not be doing the job.
Right, okay, so you left out the details. So that's exactly what's going to be wrong with this lecture. It's a grotesque simplification, full of inaccuracies, full of overstatement, full of not being the truth. And so what's the point? If this is your best effort at getting it exactly right, then of course physics is going to get wrong answers. Because clearly you don't care about being exact about a damn thing.
But this thing is completely characteristic of all of the particles of nature and is a universal character.
All right, so again, this application, because there's a little seems like it's all exactly like. So they're saying that what electrons do is exactly the same thing as photons do. They're made of the same thing. They function the same way. And then a big giant atom is doing the same thing for the same reason. Might be a similar pattern. But you can see in the results that the patterns aren't very similar. They're quite different in detail, and even in gross appearance, their differences are apparent. So there is no sameness. The pattern between the single slit and the double slit has a gross appearance of the same thing, but it's once you see past that, there's no similarity at all. In the sense that they're fundamentally different.
And it is, if you want to hear about the character of physical law, essential to talk about this particular aspect. So it will be difficult. But the
difficulty is is just keep everything so general and make up parts that you have to fill in the blanks with made up stories, and you can make it sound like you got some sort of reason to believe. But if you really draw the real patterns and you draw the real circumstance and you try to make the dots connect, they won't connect. So if he puts the real evidence down as real dots, he can't draw the picture of his gremlin. It's only because he keeps the dots on separate pieces of paper and puts them in different perspectives that he breaks the continuity of the image.
Difficulty really is psychological and exists in the perpetual torment that results from your saying to yourself, but how can it be like that? Which really is a reflection of
Right, and it's just knowing that that can't be the right answer. Green giant eating shellfish is a silly story. There's got to be a better answer than that. Come on, we can do better than that. Yeah, and again, you can. I did it. All you have to do is start drawing the pictures. All I have to do is draw that polarized light that is 1 trillion times bigger than the electron. And I can sort of understand that it doesn't make any sense that this big giant thing is going to reflect off this little tiny thing. That doesn't make any sense.
Controlled, but I say utterly vain, desire to see it in terms of some analogy with something familiar. I will not describe it in terms of an analogy with something familiar.
Well, of course you will. So it's hilarious, right? Because he's going to go through the process of explaining it by comparing it to bullets and then water waves, and then he'll say, see, light does the same thing.
I'll simply describe it. There was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time.
So he brought that up, right? So he brought relativity up again. This another junk theory, in my opinion, making predictions that make no mechanical sense. That somehow you can change how time happens in the universe. That is, how long a photon takes to travel from point A to point B somehow changes because you change your perspective, your view of it. No. It took a certain amount of time, and it just doesn't matter. Your perspective is irrelevant to what actually happened in the actual universe.
And there might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people kind of understood the theory of relativity in some way or other. But more than 12.
Yeah, they understood it as a bibbly-babbly, wooey little pile of nonsense, and oh, that's what apparently people want to believe. Clearly, religion caught on. It doesn't make any sense. It's silly and stupid. You know, you would think people would reject it just because it's imposing all of this blame. Like if my kid is born retarded or something, I did something wrong. I mean, some clearly people with insane guilt complexes or willingnesses to accept guilt complexes or something. They invent a god. It doesn't seem like any person I'd ever want to know. A cruel, beastly, horrid, the creepiest father you could possibly imagine. And they made that reality. You're just like, they didn't even invent a god that wants to do anything fun. He's a fucking pain in the ass. A grotesque, monstrous overlord, okay, that just wants to fucking kill us for the smallest of trespass. Oh, I ate a fucking apple. Oh, fuck you. Go to hell. Fuck you. You go. I mean, why would they even accept this fucking idiotic theory? So obviously people are crazy, so they not only create made-up little wooey mush theories, but they create ones that are fucking so stupid.
On the other hand, I think I can safely say that nobody understands quantum mechanics. Now, if you appreciate...
So it's all funny. We have a completely incomprehensible, mushy pile of shit theory.
This and don't take the lecture too seriously, that you really have to understand in terms of some model what I'm going to describe. And just relax and enjoy it. I'm going to tell you what nature behaves like, and if you will...
So again, he's not going to do that because the experimental evidence isn't what he claims it is. In detail, in actuality. It's not factual. He's not going to explain what actually happens.
Simply admit that maybe she does behave like this. You will find her a delightful, entrancing thing.
So says you, right? And, so yeah, if I cut off my, penis, I'll get along with God just fine, right? Yeah. Fuck that.
That's the way to look at the lectures, not to try to understand. Well, you have to understand the English, of course. But in any sense, in terms of something else, don't keep saying to yourself, if you can possibly avoid it, but how could it be like that? Because you'll get down a drain. You'll get down into a blank binary in which nobody has yet escaped. Nobody knows how it can be like that.
Right. So I don't think nobody tried very hard, right? Because there's just no reason not to sit there and draw it and say, oh, I got to come up with a better mechanics because this thing that's a trillion times bigger than this other thing can't possibly have a personal relationship with it. There's no way the thing a trillion times bigger, is having sex or anything. Can't happen.
So then just let me describe to you the behavior of electrons or a photon in their typical quantum mechanical way. So the way I'm going...
So he's not going to do any of that, right? He's going to give us these really simple analogies, and then he's going to say, see, it seems like, so it has to be is-like, right? It seems a little bit like a water wave pattern, so therefore it's just like it.
The way to do this is by a mixture of analogy and contrast. If I made a pure analogy, we would fail. So it must be by analogy and contrast to things that you're familiar with. And so I make it by analogy and contrast first to the behavior.
And that's a good enough way to do something, but again, they don't take the analogies all the way. They don't take them far enough. And as I've pointed out, the analogies work just fine. I mean, the bullet analogy for a photon works if you understand the photon's a collection of bullets. It's a bullets happening over a period of time, and that's the frequency. Works just fine if you take it a step further, if you think a little bit more, if you actually try to draw it.
Your particles, for which I will use bullets, and second, the behavior of waves, for which I will use, say, water waves or sound waves. So we begin first to discuss in a particular, what I'm going to...
So, and the key ingredient again is to understand the difference between a wave theory and a particle theory is the fact that the medium, the photons, have to be connected to each other in the wave theory. They have to have the same adhesion that water has between the molecules. And there's no evidence that photons have any of that connected to each other, that they all drag each other somewhere, that they have any communication between each other, that they in any way know anything about each other's adventures in time and space. No.
What I'm going to do is I'm going to invent a particular experiment and first tell how it would behave, what the situation would be in that experiment using particles, what you would expect to happen if the waves were involved, and then what happens when there are actually electrons or photons in the system. And I will just take this one experiment which has been designed to contain all of the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and peculiarities of nature 100%.
Right, so he's saying, isn't this overselling? I'm going to give you this one experiment that shows it all, that displays all of the phenomenon. And then when he shows us the experiment, it's the 200-year-old version of it. Okay, it's the one that we know isn't true. We know that isn't the reality. I mean, it's almost laughable how bad this is an example. Is I'm going to give you an illustration, a long-held, really rigid, really great, and it's so archaic. It's the Model T version of the fucking Maserati. I mean, it's not even close. Model A.
Any other situation in quantum mechanics, it turns out, can always be explained afterwards by saying, you remember the case of the experiment with the two holes? It's the same thing. And so I'm going to tell you about the experiment with the two holes, which is the general mystery, does contain the general mystery. I am avoiding nothing. I am bearing nature in her most elegant and...
So again, I'll just point out for the sake of the clarity here, I'm not hiding nothing. I'm showing you it all. I'm giving you the truth. I'm dealing with the real experiment. I am getting right to the core of the substance of this thing. And again, the key thing they discovered since Young, I don't even know how they didn't know it back then, is when you really do this double-slit experiment, there's only one circumstance where you don't see an obvious pattern problem, where there's two patterns. There's two patterns happening. Okay, there's two patterns. Okay, there's this pattern, the spacing between these little blocks, and then there's this obvious thing where this block is missing and this block is missing, and you have this other pattern. Okay, that's the two-slit pattern. That's the real thing that happens, and the only way you can make that pattern not show, that is, this X you won't see this, is if I make this slit intensely small. But anything above a couple of wavelengths, of distance, and this shows up. This is a reality. So that's the real pattern. That's the real, that's the real seashell on the frickin' mountain. Is this? What the hell is this? What is this? What the hell is this doing there? How does that happen? Because Young's drawings won't make it, right? This little silly wave crap won't work. Okay? This doesn't work anyway, to tell you the truth, okay? These things aren't really in the right positions, but anyway, for if you use the distance being the center of the slit, this pattern isn't right. It's not in the right place. These little bars aren't in the right place. Generally, it's close. It seems like it's pretty close, but they're not right. Okay, anyway. And they don't explain that. And as I've pointed out, it's so easy to explain. It's so easy to observe it. It's so easy to just do the experiment and see what happens. And as you change the distance of this impediment, you change where these X's are going to be. You change this hump. These humps get bigger and bigger and bigger as I make this impediment smaller and smaller and smaller. The bigger I make the impediment, the narrower I make this, bits, these clumps. All right, and the wider I make the total experiment, that is from external slit to external slit, the smaller these little bars get. So if I go wider and wider and wider, I get smaller and smaller and smaller little bars. And so clearly, this is about surfaces. This surface makes a contribution. This surface makes a contribution. This surface makes a contribution. And then this surface makes a contribution. That's the math that works. All right? The only math that works. That's mechanically what's happening. And you can't put your waves there. And even if I did put waves there, it wouldn't work. Well, you know, if I did actually put waves there, it would work. But, I mean, you can't put a wave there. There's no way the wave would be here. There's, you know, I mean, you logically know this, right? I mean, you know the wave has to be here. The wave can't be here. The center of the wave. But as it turns out, this is the place. The surface is where it's happening. This is the event. The surfaces are the event. The obvious answer, the intuitive answer, the surfaces causing the effect is actually the answer. And they are running from that truth. That truth existed 200 years ago. That truth existed even when Newton existed. Was this idea that you could draw these simple lines off of the surfaces and say, well, what if the surface is moving the photon in these different directions? And then the only complication is understanding that the photon is a composite object, and I could actually take, you know, I could take bits from two different photons and I could mix them to create a new photon. You know, that I can take parts of a photon and rebuild a photon. And that's the only other element you need. And you have that's the complete explanation, completely mechanical, doesn't require any woo or magic. I don't have to make any spontaneous, or I don't have to invent any magical laws of uncertainty. Yeah.
The difficult form. They start with bullets. And all the experiments are going to be in the same general design, so I'll draw it this way. Suppose that we have some source of bullets, which is just represent the source, which we call the source, and is in fact, in the case of bullets, a machine gun. Then we have a plate in front here with a hole in it for the bullets to come out of, and this plate, in the case of bullets, is armor plate.
All right, so this is a piece of the experiment, it's completely superfluous to the experiment nowadays. Nobody even puts that first hole there anymore because we have laser beams, so we don't even bother with that nonsense because it's a nonsense. And it already breaks your light, right? We already know that a single slit is going to create a diffraction pattern. It's going to spread the light, and it's going to spread it in this same kind of bar-like manner. It's going to be places where there's going to be more photons and places where there's going to be less photons. So we already know that that first slit is already breaking light. It's creating photons that are, in pieces, fragments.
Then a long distance from here, we have another plate, which I'm drawing.
So the idea would be is that the hole's purpose, okay, and it's a useful purpose. So don't get me wrong. Even though it's diffracting the light, it's breaking photons. What it's also doing is giving you some hope of having light that is more similar and consistent. So the idea would be is you put a slit here, because when the light's coming out, it's doing this. And what you want to do is get it to be as parallel as possible. So you want the light that actually goes into the experiment, you want it to all be as consistent as possible. And so the idea is that, yes, the longer I make this distance, the more likely that these beams of light will be close to parallel with each other. So I have a straight kind of frequency. I have them in phase. So the more likely they're to be in phase if they traveled the same path length from the source. So that's what the first hole was in the past used for, is because you were using sunlight that was coming in all kinds of rays and blah, 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 different things. And so you wanted to get the real parallel beam. And so that's what it gives you to go into the experiment. So you send your light as consistent as possible into your double slit, because you want as clean a wave as possible to do your experiment.
Going only a short distance because I haven't got room on the blackboard for everything, but this distance is supposed to be much longer in proportion to the width. Please expand that. That's a small point. And it has 2 holes in it. That's the famous 2-hole business. I'm going to talk a lot about these holes, so I'll talk about this hole as number 1 hole and the other hole as number 2.
Right, another problem in drawing it, that obviously these holes look like they're at bizarre angles from this hole. But the truth is that this hole is the same size as this experiment, essentially, and so this should be drawn as 2 little tiny things right here, and it's, you know, there is no angle that the light's going at an angle to get to this hole or an angle to get to this hole. That's not part of the reality. So, you know, it gives you an optical problem right from the start.
And I'm only drawing it in 2 dimensions. You can, if you wish to imagine these as round holes in 3 dimensions, but just say this a cross-section. And then again a long distance away, but we'll draw it relatively short distance because of the limitations of this blackboard. We have another screen here, which is just a backstop of some sort, on which we can put in various places what I will call a detector. And we'll mark that detector.
Right, now, so this is another one of those, like, you know, kind of obvious... You should be able to figure out without too much thinking about what you're actually causing, you know, at your slits. And even if you were thinking of it in terms of waves or whatever you're thinking about what you're creating, the idea would be is that you know something's going to come out of this thing in these kind of rays or ranges. Okay, that the experiment's going to do that. And here I am taking a flat screen, which I know from a movie projector, I know from lots of things, starts distortion. As you go out here, I'm distorting the image. And the only way I can see the image as it actually is that I would have to put the screen on the same arc as the experiment is being conducted, so that these lengths, these distances are the same. And this is the same distance, and this is the same distance, and this is the same distance. So when I make all the distances the same, then it becomes really obvious that all I have is this 90 degrees here. You know, I have the 180 degrees of this whole thing, but that's all I have. And that whatever happens, there's a finite amount of it. I can't shoot something for a long, long time and hit way over here on the screen. None of this whole idea of this infinite plane that I'm broadcasting this thing on, that distortion goes away when I tighten this up and realize I should be doing the experiment with all these rays traveling equal distance. And, you know, equal distance from the... Obviously, this ray is a different distance than this ray, and that's why there's a pattern, but the point is equidistant from a center point. And when I do that, I can see that these are just notches. And that these notches, this number of notches, will completely correlate with the number of notches here. How many wavelengths of light do I have in there? Well, these will correlate exactly. Okay, the notches in here will correlate exactly to the notches here, in the sense that it'll be a pair. Whatever this is, you just double it, 2x, okay, for both sides. It's going to send stuff, it's going to send this image to both sides. And that's what you're going to get. And that this center impediment is doing exactly the same thing. That it's just going to say, how many wavelengths do I have in here? How many in this distance? And that will be my second pattern. Okay, is those wavelengths. And that's it. Now we're all done with the experiment. We know that this distance will dictate how big these contributions are, and this distance will dictate these bars. That's it. We're done with the experiment. All we're saying is that when you combine the big bar and the little bar, you get light. A photon is made there. The photons are made there. Photons will be seen there. And photons will be seen there. But you won't see one where the big bar, okay, doesn't exist. Where the big bar isn't shining any, or throwing any parts, the little bar, even though it's going there, can't make a photon there because it needs the other half of the equation. It needs the other 2 contributors. And without them, it can't make a contribution. It needs those other 2 to be in phase for it to add more in-phase bits. So there's no light there. That's it. Done. And it's just about drawing it right. Once you curve that line, you know, oh, it's a limited amount of space. There isn't an unlimited number of bars I can make. There isn't an unlimited place I can broadcast it to. There's a very finite number of angles. And that's it.
Which in the case of the bullets is a box of sand into which the bullets will be caught, and we can count them. That's the detector for bullets. I don't want to have to redraw the experiment each time, so I'll label everything in this way, and then we'll be able to catch on to situations for different cases. And also, I'm going to do experiments in which I count how many bullets come into this detector, or box of sand, when the box is here, or here, or here, or here. And to describe that, I'll measure the distance of the box from somewhere down here.
So you could really understand it if you actually thought about bullets, because you think, oh yeah, the bullets are going to run out of momentum, with distance. So when I put this box way out in the periphery, the bullets would never get there because they'd run out of momentum. And so you could sort of understand, oh yeah, this is about angles, and it's about the bullets really going there. If I want to detect all the bullets, well then I just arc this, and I'll detect all the bullets. Every single bullet will have to be detected, and I just run my little box on that arc. And I detect every single bullet that way. I don't miss any.
Call that X, and I talk about what happens when we change X. It means only you move the doggone thing up and down. All right. Now, first, I would like to make a few modifications from real bullets into idealizations. The first is that the machine gun is very shaky and wobbly, and that the bullets go in various directions, not just exactly straight on and bounce back.
Yeah, they don't do the same thing every time, and therefore they don't do exactly the same thing in their outcome. So if I vary the source, then I vary the outcome. But the argument would be, yes, if I actually could shoot them straight, and I shot them through one hole, and then I shot them through the other hole, okay, no magic, no mystery, I don't break any rules of the universe, and I'll get the same exact pattern. The same exact thing will happen if I can, but obviously, I'm arguing that these are parts of photons, so more than one photon has to be in the experiment. And I'd argue that's the flaw of all the experiments ever done where they say a single photon, because they aren't single photons. They're only single photons because they're saying, well, it's the smallest amount of photons that'll actually recreate another photon. So they're doing the experiment. I've explained this before, and it's worth stating because this isn't that complicated, right? You're trying to do a controlled experiment to see if you're actually shooting one single photon at a time. So in space, there's only one photon at a time. And a photon, again, is a composite of bits in a certain length. Okay, it has a ray length, whether you believe in a wave or not, whatever. And the way I have to do the experiment is that I have to do it without the experiment in the way, right? I can't put a slit in here and then say how many photons reached here, because the slit could, in fact, be taking two different photons and taking the pieces from those two different photons and sending them to a location and making a new photon. So two photons need to be in the experiment at the same time, or I won't get any photons at all here. So you first do the experiment in a controlled way where you say, okay, let me make the gun where I can see a photon on a plain screen and I get actual dots from a photon. All right, and dots, and that's it. Okay, then I know I have, and they're coming, one every second or something. Doesn't matter. And so I know there's only one in this space at a time, and only one in this space at a time. And then you put your experiment in here and see how many photons you get. I would predict, if they ever do this, I will predict, if they do the experiment right, make a gun that's shooting photons once a second, landing on the surface, and then they put the two slits in there, they will get 0 photons. None. It won't be enough photons. You can't do the slit experiment without this. You won't get any pattern at all. You'll get maybe a photon will hit here now and then, hit here, hit here, hit here, hit here. Maybe a photon will hit here now and then. But that's it. You won't get any pattern. And that's a basic controlled experiment to find out how your instrument works, a basic test. Again, no LIGO tests, no test of anything they ever say these devices are doing what they're saying they're doing. There's no test showing them doing it. There's no verification that that's what it actually does. And here, the simplest experiment the simplest even concept of a single photon gun, and they don't do it in the proper order. They don't show that the gun is actually doing what they say it's doing. It's just pathetically bad physics. All right, so maybe this is a good enough place to stop, and we'll continue, and I'll restate some of the same things all over again in the next version and in the next version, and just keep reiterating and re-emphasizing the point. Their evidence is weak, it's sloppy, it's even ugly. Some of it is overtly made up, experiments never conducted, and conducted very badly, in a circumstance where they didn't go to the trouble to first prove what their instrument was doing before they say what actually happened. Prove that your gun is doing what you say it's doing before you tell me what happens when you put something in the way of the gun, that kind of thing. They don't even follow those simple rules. And in defense of a theory that's extraordinarily silly, that is green giant retarded as an explanation, it doesn't explain the phenomenon well, it doesn't explain it coherently, it doesn't explain it mechanically. It is a religion. Okay. Till the next time. Such.